Hello, once again, class. This is part 2 of your notes for 2.5. So last time we looked at the zeros of a polynomial function, how to find those on your calculator using technology to help you. But the problem is what we're doing visually is finding the location of the zeros of a polynomial function. So let's say hypothetically this polynomial crosses right here at -5, -2, and 2. And this is a degree 3 polynomial. So we found its 3 zeros we talked about last time. And these 3 zeros would show up on the calculator. Okay? They're rational. Alright, and even if this, this one over here hypothetically was, a half, it would still show up on the calculator. Right? But the problem comes in when the fact that a polynomial, it can cross anywhere. It doesn't have to cross at whole numbers. It doesn't have to cross at fractions. I can pick this polynomial up and move it. And now maybe it crosses, maybe this, instead of it being -5, -2, and 2, now it's like the square root of negative square root of 5, negative square root of 3, and the positive square root of 7. I don't know. I'm just making up some numbers. It doesn't have to cross at rational numbers. It doesn't have to cross at a fraction. It can cross anywhere. All right. It can cross the way they behave and their orientation. They can take on a lot of different forms, and they can cross at different places. So we're not always going to get whole numbers, and we're not even always going to get fractions. So we have to still be able to find these places where it crosses, right? And that's what this next set of examples is for. All right, so what we're going to do is we're going to type in the function into our calculator, and then we're going to find as many zeros as we can with the table. The method that we're always going to find as many as we can with the table, because that's just going to make your work the easiest. So I'm going to go back and make this 0 and 1 from the table. Anytime you start a new polynomial, you should always start your delta table back to 1, and your table start back to 0. And then we go to the table and we look. Alright, if I scroll up to -3, there's where that 0 is. So I've got a 0 and -3, but if I just keep scrolling, I'm not going to see any more zeros. Okay, table set, back to 0. Same thing if I go down. I'm not going to see any more zeros that way either. Okay, and you can always graph it to kind of get a visual and see that. Zoom 6 here. So there's our -1, 2, 3. There's our -3. There's another 0 there, another 0 there, but I see all 3 zeros in the screen. I see the 2 bins because this is degree 3. Remember, there can be at most 2 bins. I see the 2 bins. I see the falling to the left, the rising to the right, which would be the end behavior here because of that leading coefficient. So I've got a complete graph. I know that if there were any more zeros, it'd have to be in between -10 and +10. And when I scroll back and forth on the table between those numbers, there's 12. I haven't seen a 0. There's the -3, 0. And then there's -10. I still haven't seen a 0. And again, because of the graph, I know the end behavior. It's going to keep falling and keep rising. It's never going to hit again. So these other zeros aren't going to be whole numbers. Alright, but look. Remember what we said last time. The leading coefficient is 1. So the only potential rational zeros are whole numbers. -3 was 1. That means the other two are not rational. They're going to be irrational zeros. So what we do in that case, once we've found a rational zero, if the others are going to be irrational, then we use synthetic division with this zero as the number that we put in the little box. And we're using the factor theorem. If you recall the factor theorem from the last section, it says if c is a 0, if we know, and we know negative 3 is a 0 of this thing, so if plugging in some value c is a 0, then x minus c is a factor of f of x. So when we divide, when we do synthetic division and we're dividing by this, what we're going to get is a factor, another factor too. I mean, if x minus c is a factor and I divide the function by that, then I get a second factor. So in this case, when I divide by negative 3 right here with synthetic division, I'm dividing the polynomial by x plus 3. And if you remember, when we divide a cubic, degree 3, by a line, x plus 3, we're going to get a quadratic, x squared. So that's the idea. We want to do synthetic division until we get degree 2, right? Sometimes it'll take more than one synthetic division step, sometimes it'll only take one. Just depends on what you start with. If you start with degree 3, it'll only take one iteration of synthetic division. If you start with degree 5, it's going to take 3. Alright, so let's put these coefficients in. I've got a 1x to the third, 7x squared, 11x, and a negative 3. Alright, and we're going to bring down the 1 to start everything. Okay, and then negative 3 times 1 is negative 3. Add these, I get a 4. Negative 3 times 4 is negative 12. Add these, I get a negative 1. And negative 3 times negative 1 is 3. Add these, I get a 0 remainder. Remember, that's expected. If 3 is a 0, then the 0, whatever we get when we plug in that, should be the remainder. Okay. So remember, this was x cubed, x squared, x and the constant. So now this is 1x squared, just x squared, 4x plus 4x minus 1. Alright, that's a remainder of 0, which again we don't have to put it. So what that means is, so far, this function, x cubed plus 7x squared plus 11x, since negative 3 was a 0, that means x plus 3. Remember, this is the thing that makes a factor of this equal to 0. So negative 3 makes x plus 3 0, which makes this whole entire thing 0. So that's a factor. Again, that's what the factor theorem says. And then that means this here is a factor also, because this is what we get when we divide by this. So x squared plus 4x minus 1. So this polynomial has this factored form. Alright, now, earlier techniques you would try to factor this, if you could. But if you could factor this thing further to solve it, then those things would show up in the table. Since they didn't show up in the table, negative 3 was the only thing that showed up in the table. That means this thing right here won't factor any further using normal factoring techniques. Or we can get it to factor further, it's just not going to be with rational values. Not going to have any rational numbers in it. So what we have to do to solve this, to find all the zeros, which we're told to do, since this is quadratic, we'll have to use the quadratic formula from this point on. Alright, now remember, we're finding the zeros of the original polynomial, this guy. Okay, but what this says here is any zero of any factor of the original polynomial will also be a zero of the original polynomial. Okay, meaning since we know now that this thing, because of the factor theorem, this negative 3 is a 0, that means x plus 3 is a factor. And because we divided, we did it synthetically, but we divided by x plus 3, we got this polynomial out. So because this thing is equal to this, which has multiplication, if I make this equal to 0, like I did with negative 3, I get 0 times something. And 0 times anything will be 0. So negative 3 makes this equal to 0 because of the multiplication. Likewise, anything that makes this equal to 0 will result in multiplication times 0, and we get another 0. So that's what we're trying to say here. Any 0 of any factor of the original polynomial, any 0 of this, because it's a factor of the original polynomial, will also be a 0 of the original polynomial. So now we're going to try to find the 0 of that factor, x squared plus 4x plus minus 1. Because this is quadratic, we can do it with the quadratic formula. So in this, a is 1, b is 4, c is negative 1. I just plug those in to the quadratic formula and then just simplify it. All right, 4 squared is 16. Negative 4 times 1 times negative 1 is positive 4. Over 2 times 1 is 2. All right, and then simplifying that, 16 plus 4. All right, I get 20. All right, and then we have to simplify the radical. All right, it's very important that you know how to simplify radicals. So 20 is not a perfect square, but it does have a perfect square factor, meaning a perfect square does divide 20, and that perfect square is 4. So we'll write 20 as 4 times 5. All right, and then the square root of 4 is 2. So we end up with negative 4 plus and minus 2 times the square root of 5 over 2. And now what we're actually doing here is, because negative 4, 2, and 2 all have a common factor, I'm going to pull a common factor of 2 out on the top. So factoring out a 2 on the top will leave me with negative 4 divided by 2 is negative 2, plus and minus 2 square root of 5 divided by 2 is just 1 square root of 5, or just the square root of 5, over 2, and then these 2's cancel. So we end up with x is equal to negative 2 plus or minus the square root of 5. Now, remember that's 2 zeros. There's a plus, there's a minus. So what we have here is our solution set is negative 2 plus the square root of 5, comma, negative 2 minus the square root of 5. Okay, there's always 2 there. The plus and minus is because when you have the quadratic formula, these last 2 zeros are going to be like the same distance away from this, whatever this number is, negative 4 over 2. So there's the negative 2, and we add square root of 5. There's negative 2, we subtract square root of 5. So that's what that plus minus means. You actually have 2 more zeros here. So what is our solution to this thing? Well, we know what we just came up with was a solution. So negative 2 plus the square root of 5, negative 2 minus the square root of 5. But this was degree 3, so don't forget to go back and pick up the original. Negative 3 was what got the ball rolling. That made the y 0. So negative 3 is also a solution to this equation. Alright, so just a reminder of the process. Look on your calculator. Find the 0 from the table. You may have to adjust your delta table to find that first 0. Once you find the first 0, synthetic division to get you down to a quadratic. Once you find a quadratic formula, and making sure to simplify any radicals that show up in the quadratic formula. Alright, there's this website called Google. Just kidding. But if you go there and type in simplifying radicals calculator, so you can type in here what the radical is. So in that last example we had the square root of 20, and it shows you the process. Okay, square root of 20, that's 4 times 5, square root of 4 is 2. Okay, okay, you can type in any expression, anything that shows up in these. Okay, so just know that that's there, and it was the very first thing that popped up on Simplifying Radicals Calculator.